in undergraduate also. And if we say L is much greater than T, L is the width, okay? The length is B. Hope everybody remembers that. Then we get P approximately 2L, and then we get this sort of expression for QF. Same as this one. And so this is a QF expression which is just for a thin fin, that's all. This is only where my pointer is. That's the expression when the fin is thin, that's all. But the last expression that you see on the slide, that is written in terms of AP, which is the profile area. Profile area is B multiplied by T. So this is B, and this is L, this is of course T. Now, when we write it in terms of the profile area AP, the advantage is that we can also consider situations when AP is a prescribed number. Okay. So let's say you want to spend this much amount of material in building the fin. Then that means that's a particular volume, right? And from that we can say that, okay, this is like a particular profile area. So that particular profile area can be fixed, and then we can do some optimization with respect to that for that particular profile area. Now, what we saw is that, okay, this is again the thin fin expression, the first one, and the second one is in terms of AP. And I had plotted this, both these expressions in class, and we saw that the first expression, equation 2.32, that just shows a monotonic increase in heat transfer with increase in fin thickness. Okay, and the second expression gives you a peak in heat transfer QF, and then it falls down, right? So the optimization is obviously possible for the second case. Second case is the profile area is prescribed. Now let's try to understand this. Before we go further, let's try to understand this in a bit more detail. Okay, so the first one, the thin fin, just a thin fin. Actually, this is also thin fin, but this is written in terms of AP. Okay, these expressions have been obtained after making the thin fin approximation. And when we increase the fin thickness, it's understood that it still remains thin. Okay. So what does it mean? It means that when the fin thickness is very small, left hand side, the coordinate, then of course it's very thin, hardly any thickness of the fin. Then towards the right hand side where my red pointer is, there also the fin is still thin, okay, even though that thickness is much more than the thickness on the left end of the axis. Okay, now the first curve. Why does the heat transfer increase as you increase the fin thickness? Just physically, why does it happen? Not using these expressions so much, but just you don't need to use 2.32 so much, okay? But physically, why should increase? Why should it increase? Why should QF increase with T? No idea. You studied fins in undergraduate. You studied for GATE examination. We did this in class, in the last class also on Friday. You still have no idea why QF increases with thickness. Physically, okay. One can always derive expressions and then okay, check the expressions another time, but physically. Hmm. No, I'm not talking about this curve. I'm not talking about the solid line curve. I'm talking about the one with the dashed line. Equation, the one with the dashed line which says 2.32, the upper curve. So maybe you can think about it like this, that this is, let's say this is the fin is a fin of a particular length b. Okay, if you have a fin of a particular length b, if you increase thickness, why should the heat transfer increase? Yes, so it increases area, isn't it? So the your perimeter is this one, and the area which gives you the heat transfer is that perimeter multiplied by b, isn't it? Actually, there's this one also, but it's basically that area, that surface area is p into b, right? Plus the this thing. Right. So if you're increasing thickness, you're increasing perimeter, so this area is going to increase, and then you are likely to get more heat transfer. Okay. But it increases very fast for small fin thickness, and then it tapers off. Okay, it doesn't increase much when the fin thickness is little larger. So what's the physical reasoning for that? Okay, since we have shortage of time, I'll give you the answer because I don't want to, I can't afford to wait for too long because I have other topics to cover also, right? But these are things which you should think of. One can always solve examination problems and problems which you get in GATE, okay, by knowing some formula, putting some values. This is thermal conductivity, okay, this is heat transfer coefficient. Those things will work. But I want you to develop a physical feel for this one so that when you become a designer working in an industry, you can kind of know that, okay, in this situation, this fin will work, that fin will not work, whatever. Okay. It will come from a feel. Right, so this fin temperature will of course drop with distance. There is heat transfer by convection, but there is also a conduction resistance. When you add this solid material to this is your wall, which is at a high temperature. When you add this solid material, it will result in decrease in temperature, isn't it? Outside of this building is cold, but inside is hotter, so it's like it can be warmer inside, and then the temperature drops through the wall because of the resistance, right? So we all know these things. So when you introduce a fin, you are also introducing conduction resistance, which will result in a drop in temperature. And if you have a higher fin thickness, what will happen? Okay, so the temperature will be such that the heat transfer will become less as you have higher fin thickness, correct? So is that all right? Yeah, the temperature is outside is T infinity, that we are not changing. So if you talk about temperature, I'm actually talking about the temperature of the fin, right? Okay, so the first curve, I hope you understand. The second curve is that the temperature rises and then it drops. Second curve. So why does that happen? So the second curve is plotted using some value of AP. So let's say AP equal to 5 or 10 or whatever. We have that number. And that means you have prescribed AP value. Now AP is just this area. So this is AP. This is B into T. Okay. So when we are talking about the second curve, it's like as you increase the thickness, moving towards the right hand side, this plot, towards where my pointer is, and then B will correspondingly decrease. Okay, so keep this picture in your mind. So you have a thick fin with small length, and then we also have a thin fin with a much larger length. Okay, so this one is at the right hand side. Okay, large fin thickness, and this one is at the left hand side of this plot. Right hand side, left hand side, I mean here. But this thing is this one, and this thing is this one, right? Now you tell me whether the plot makes sense or not. Whether there should be a peak or not. So, okay, let me try. We try showing it here. So if you have a fin which kind of looks like this, is it a good thing? No, because that plot says so. But physically, you want a physical answer. The answer is like this. If you have made something like this, this one, then it's kind of like the bare wall, right? It's kind of like the bare wall. So imagine going to the extreme left-hand side of this plot, then the thickness is almost 0, right? So then, this becomes even smaller, so it becomes almost like a wall. Then the heat transfer is not good, no? Heat transfer improves when you add fin. right? Okay. And what happens when we drawing on this one is difficult, but I'm just trying to draw this. Actually, I should have drawn it thinner, but you get the point, right? A thinner film which is longer. Then heat transfer coefficient will still be small. Sorry, not heat transfer coefficient. Heat transfer again will be small, isn't it? Small fin thickness, but a large length. Okay. As I said, should I draw it again? I couldn't draw it properly. Imagine this length to be smaller. This thickness to be smaller. Then again, heat transfer gets affected because you're not giving that much area. So this is this extreme. This one is this extreme. In between, you will get a peak. Okay. All right. Now I hope you have got some physical idea, but all these equations, equation number 2.32, 2.34, these are from H.S. Lee's book, Ho-Sung Lee, that is what his name is. So you will get these there, but the physical explanation is not given there. So that you have to play in your mind, like the way I'm encouraging you to do. So do that and then understand this one. Okay. And then the next thing that we'll try to do is that we'll take this expression and then do a dqf dt of this one. dqf dt. So we are trying to, since we have already plotted and we have seen that second curve with a solid line has a peak, so we know there is an optimum. So we can have an optimum thickness at which the heat transfer will maximize. So we do dqf dt equal to 0. This I will not do in class. This you will be able to do because this is just simple differentiation. And once you differentiate, then okay, then you will get something like this equal to 0. So this is dqf dt equal to this. We set this equal to 0. So that means just transposing and all that we get this expression. And here we define beta equal to mb. mb is like your ml that you saw in your undergraduate, and that thing is just this quantity. Now m has been written in terms of mb has been written in terms of h and k. Isn't it? M remember, m is m is square root of hp over kac. Okay. So P is, this P is approximately 2L for this case when you have a thin fin, right? And AC is L into T. So if you write these, then it can be, M can be written in terms of H, A, L, and T. And then you can get the last expression if you write MB in terms of AP. So all these things should be possible for you to do. So look at this, then the left hand side becomes 6 beta and the right hand side becomes sine hyperbolic 2 beta. Okay. Now we will go to, we'll just plot this. Okay. So we have 6 beta You have 6 beta equal to sine hyperbolic 2 beta, and just try to solve this. Again, this can be done approximately using a graphical method, and you can download GeoGebra and then you can just try plotting this, or you can use any other software that you like. So we have 6 beta is equal to sine hyperbolic 2 beta. So we'll do y equal to 6x. So this is one equation, and the other equation is y equal to sine hyperbolic 2x. So these are the two curves. It almost didn't take me any time, and you can see that the solution will be the point of intersection, obviously, and that is see, this is going to be between 1 and 2. This is 1.2, this is 1.4, and this will be around that, okay, around 1.4 or so. Now there's a way of zooming in onto this. No, what did I do? Okay, this is about 1.4. Yeah, there's a way to get the intersection point also, but I forgot how to do it. You can explore the software or any other software to find out how much exactly it is, but it's about 1.4. Let's go back to the PowerPoint presentation that I was using. So the number is 1.4192. Graphically, it seems like about 1.4, so it's 1.4192. This is beta. And actually, you can also see that the efficiency of this fin, efficiency formula you learned in undergraduate. So this is tan hyperbolic mb divided by mb, and that turns out to be 0.627. Efficiency turns out to be 0.627. Okay, so what have we done? We have got this optimization done when the profile area is prescribed. AP is prescribed, given number. You have given some number for AP. For that, you have done that optimization and then got beta equal to 1.4192. But ultimately, it's not beta we are interested in. We are more interested in B naught and T naught, where B naught and T naught are the names for the optimized value of B and T. AP, of course, AP is B into T. And when you optimize, then the optimized values are B naught and T naught. So once you have this beta to be 1.4192, then beta is m b naught, and this is m. A little bit of rearrangement. This is T naught to the power minus half, these two together, which was there in the m expression. So from this you can get T naught. So from this expression you can get T naught in terms of beta. Beta is not a problem because beta is 1.4192. We've already obtained that. And we can also get B naught. How? From this expression. right? So these are expressions when you had a prescribed value of AP. Now we'll also talk about what is given in the book as constant heat transfer from a fin. So what's this? This is, I mean, we have to keep these curves in mind and also these two expressions. Actually, what you can do is you can write these two expressions on your copy, and you already, I hope you've already sketched the profiles in your copy. Okay, and after these, we go to this discussion about constant heat transfer from a fin. Now, what is this? This is okay. We have this QF versus T, which we saw is kind of like goes like this when the profile area is constant. And so what is this constant heat transfer? Constant heat transfer, he calls it constant heat transfer. I don't actually like this. I think we should say that this is a prescribed heat transfer value. So we got a fin which we have optimized, right? So we've given some value of AP, and then this gives you some maximum heat transfer. Given a value of AP, you got some maximum heat transfer. But in this particular case, we are thinking about, okay, that AP situation, optimization with with some AP, but we are also thinking of, if we provide the value of QF, if you want a certain value of QF, right, then what should be the dimensions of the fin? If we think about a given value of QF, how do we get the fin, optimized fin dimensions? So that can be interesting, because you have this surface, you want to attach this fin, and you want some value of heat transfer. You don't want a small value of heat transfer, you want a significant value of heat transfer. So you're prescribing that you want this much amount of heat transfer, right? Suppose we are talking about that case. Now, this QF expression is which expression? This is the first expression or the second expression? First expression. So this is the expression where we have just assumed a thin fin. We have not done anything else to this expression. Correct? And then we say that QF is equal to this. This is M, this is B. So MB is beta, right? And we say that for beta, we will use 1.4192, that optimized value. So if we have beta equal to 1.4192, then tan hyperbolic 1.4192 is 0.8894. So it's just 0.8894. Now, how do you get the optimized fin thickness? So the optimized fin thickness will be obtained from this expression. So we do this tan hyperbolic expression, we just use 0.8894. This whole thing becomes 0.8894. And this has got a t to the power half. So we can write an expression for t to the power half in terms of this QF and other things, including that 0.8894. Correct? So this becomes your T naught. And a little bit of simplification, this you get this 0.632 from here. So this is T naught. Now how do we get a B naught? So beta is, again, this is M, this is B naught. So from here, if we do a little bit of rearranging, we get this, and then from that we get B naught like this. So can you quickly check these two steps just to get you going? And just check whether this is all right. Starting from the first expression. Yeah. Now this is trivial, but it's, I just wanted to check whether everything is all right. All these numbers, like you get this 0.632, then finally we get 0.798. These are all okay, isn't it? You are all of you getting this? Now let me quickly just revise what we just now did, in case it's confusing. It can be a bit confusing. I'm saying that the book says constant heat transfer from a fin. I don't think that's really that helpful to understand this problem situation. What is constant? Constant with what? Heat transfer is constant. That's what this title says. Constant with what? If you take any fin, okay, there is a certain amount of heat which is going from the base, right? And that gets dissipated by these surfaces, right? So this is a constant number anyway. If you have a fin, this is a constant number anyway. So what is this constant heat transfer fin thing? Actually, what we are doing is we are saying that, okay, we want some amount of heat transfer. We are giving some number, okay, so many watts. So instead of constant, I would like to say that this QF is prescribed. Like a doctor prescribes you medicines, this is somebody has prescribed, okay, I need this much amount of heat transfer, okay, all right. Now you say that to get that much amount of heat transfer, I want an optimized fin, because this QF, maybe it will come from various fin profiles, maybe some long fin, some short fin, some fin with larger thickness, some some fin with smaller thickness. That's possible, right? They will all carry QF. But we want to have that optimized value of B and T, which will give this prescribed value of QF. You're being able to follow what I'm saying so far, isn't it? To do that, we'll say that, okay, we'll want to pick up this value of QF basically. This value of QF gives you optimized, this one, this gives you the optimum T naught, and correspondingly there is a B naught also. So I'm saying that once you have QF, you can actually get the optimum dimensions using the theory that we have already learned. Okay, that theory tells us that beta is 1.4192. Right? So we use 1.4192 here to get this 0.8894, which goes into this, and then you write thickness in terms of QF. So whatever QF you want, you get a T naught, which is an optimized value. And that optimization we have already learned in the previous derivation. Okay, so that is the T naught. And we also get a corresponding B naught. B naught is calculated using T naught actually. Beta is M B naught, and so we have T naught here also. And with a little bit of work, which you just now checked, so you kind of know how algebraically this is derived. So you can find out what this B naught is going to be. All right. So this is the whole story. If you read the book, it might not become clear. So these require explanations. That's why coming to class is important. I think today is the attendance a little lower. I think it appears to be a little lower than last class. All right. Again, come to class because not everything is written in the book. The book is really thick, this much thick book. The book by Lee. And I discuss few things. I skip certain things because I don't have time to cover, so much material. So I choose and discuss that which is relevant to the course. So that you can only understand when you come to class. And so that's one piece of advice. The other piece of advice, which I've already given, like to repeat this every day, write a few things, go home on that day itself, have a look at the notes and do a recall. Recall is a good way of learning. If you don't see it on that day, you will lose it quickly within the next 1 or 2 days. You will lose that. Okay, then you will end up studying more before exam. So effectively, you are losing time. Okay, I know that your first priority in life is to watch reels on Instagram or wherever it is. So you lose time for that. That's much more important than this. But to save time for watching reels, you should do this more efficiently, more effectively. Now we'll do something else. So this is an optimization for constant fin volume or mass. So this is like that constant profile area itself. So the last one was constant heat transfer, which I am calling a prescribed heat transfer. Now this is like a prescribed fin volume or mass. So what's the fin volume? Fin volume is LBT. So so this is the fin volume. So this is BT multiplied by L. L is the width. Now we have QF, which goes like this. Which expression is this one? This is that 2.34. This is the expression which is written in terms of AP. All right? And this we can write in terms of the volume. So this is AP is V by L obviously, so volume by length, volume by width actually. So we write this, and then we get beta like this. So this is just the algebra part of it, and you just keep following, and whatever possible you write also. Don't have to write everything, write some steps so that when you go home you can fill this up. Now we want to get an optimum fin thickness with a constant fin volume. So the optimization has actually already been done, because that is at beta equal to 1.419. Now, how do we get this thing? This is like, just writing it here again. This is T naught. It's got something in here which I marked with that red with that arrow in that expression. So this is V by L 2 by 3 H by K to the power 1 by 3. So the question is, how do I get this? And what's the use of this? So I'll tell you what the use of this. Before we derive this, let's just read this problem. This tells you the relevance. This is from the same book by Lee. This is an example problem, so this is solved in the book. So we got a rectangular fin, the kind of fin that we have been talking about, and it's aluminium. It has got a width of L, 2.5 centimeter. It's cooled by this velocity air, and this is forced air, T infinity equal to 22 degrees Celsius. Fin base temperature is given, and only 1.2 gram of aluminium for the fin are required. For a fin, just using 1.2 gram of aluminium. Now, determine the fin thickness and profile length that maximize the heat transfer rate to the ambient air, and also get the maximized heat transfer rate. So air properties are given. Okay, so this says what? Get the thickness, get the profile length. For this case, when, okay, you are only allowed to use 1.2 gram of aluminium, so this has got this much volume of that fin, right? You know the density. So in that volume, of course, you can have a longer fin, smaller thickness, or a shorter fin with a larger thickness, whatever, right? So which one will be optimum? That from application point of view. Now, before we shift back to the derivation, let me also tell you that u infinity, t infinity are given to do what? This we didn't discuss about velocity of air over the fin, and these things we did not discuss, right? We were seeing it for the first time. What was the purpose of giving this information? 2.h convective heat transfer. And this thing, and air is flowing over this. This is flow over flat plate, right? So you can use that those correlations that we have already learned in undergraduate for flow over flat plate. We can of H, right? Yes. So let's go back to the derivation part of it. So we are getting this, and the book just leaves it here. And I did this derivation part for you. And maybe you can take 2 or 3 minutes to have a look at this and maybe also write a few things from this one. Yeah, so he has an easier solution. But let me tell you this, that if I give you all PPTs, and even if I don't give you PPTs, he forgot your name, Abhinay. So when Abhinay, let's say Abhinay sits here and takes pictures of all the slides, it's still not going to be helpful. Still not going to be helpful unless you work it out with your hand. It's not very helpful. So when you write something, there's some effect which actually plants it more solidly in your brain. So I'll tell you the picture. So we have this one. This is beta is MB. So it's B multiplied by this part is beta. Just follow my red pointer. So this is M. And from here, k T naught to the power half is this thing from this expression. And instead of B naught here, we bring in V. V is, of course, BTL, B naught T naught L, because this is the optimized value. And so we have T naught here, we have other things on the right hand side. And just a couple of steps here, we can write T naught in terms of V by L, also beta, because beta also we had. And we have H over K also, correct? And beta will use as 1.4192. And then you got this thing which I had circled in red. That one is just a number. That number, fortunately for us, turns out to be something like 0.997656. So this is like 1. That's why I said that this thing, which I had shown in the previous slide, that meaning that it has a coefficient, and this coefficient is almost equal to 1. So this T naught, the optimized value, is just this. So what did we do in this problem? Actually, we have not studied the problem so much now. I just shown you a problem statement. What we are doing is we are saying that, okay, we've just got 1.2 gram of aluminium. And for that, we are trying to optimize. Okay? So this dimension, of course, is L. So optimization will mean, so L you cannot change basically. Okay? So you are trying to change B and T. And what combination of B and T will give you the maximum possible heat transfer? You're just trying to do that. and that expression turns out to be this in terms of volume. Okay, so that H in that problem you calculate using flat plate correlation. Thermal conductivity of aluminium is known, and V is the volume which will come from that 1.2 gram divided by density. 1.2 gram is the mass divided by density, and L is already there. I mean, whatever L you choose, so that will give you the value of T naught. Okay. So this is where we will, just one more thing. Once you have got T naught, so this is T naught, you can also use this expression to get B naught, which will look like this. So in this problem, we can get T naught and B naught both. We will have a look at this in more detail in Thursday's class. Thursday, we'll just try to see some problems and do some calculations and all that. Okay, thank you.